Okay, I guess first, does anyone have any questions or comments about the exam? Comments, those are good. Uh, okay, anybody have any questions about any of the stuff we've covered so far? I guess we already took the exam on that, so no one cares about that anymore. Okay, so now we're done with 1D kinematics, and we're moving on to 2D kinematics. So particle kinematics in 2 dimensions. Have we done anything besides particles yet? Have we talked about the motion of anything besides particles yet? No, all we've done is particles. After a couple more topics, we'll get into stuff that we're assuming has length, and then we'll talk about rotations and orientations and things like that. But for now, we're still just assuming everything exists at a point. Still a lot of, important calculations are done that way, but we're losing a little bit of information doing that. What does kinematics mean? Anyone remember? Kinematics means that all you're doing is describing the motion. Everything that you're, so describing motion, everything that you're dealing with, so you're relating position, velocity, acceleration, and they're all things that you could figure out from watching a videotape, okay? We're not talking about any kind of intensity of pushing, intensity of pulling, masses, any of those things. When we start talking about that, that'll be kinetics. So describing motion. It's just relationships between things that you could get from a video camera. And up until now, we've been dealing with one-dimensional kinematics, which means that the object is free to move along a path. It can be anywhere along this path, and at whatever point it's in, it can go either direction, but it can't do anything but stay on the path, which means we're confined to, a decision at any point about whether to go this way or that way. That's all we can do, okay? And that makes the math easy because we can choose one of those directions to be called positive, the other direction to be called negative, and then all of our directions are specified by positive and negative. But now we're going on to 2D. And so now, if a particle is here, it has a whole bunch of choices where to go. It can go in any of these 4 directions and then any combinations of those. So it actually, at any point, it has infinitely many choices of where to go. So you might think, well, okay, like maybe there's some way to, like it's not immediately apparent how the positive and negative thing would work in 2 dimensions, but maybe there's some way we can squeeze that same idea into it. It turns out there isn't. Just defining positive and negative isn't enough to talk about directions in two dimensions. So like, for example, what if we chose the positive direction this way, okay? Well, that would work for saying if something's moving this way, it's positive. If something's moving this way, it's negative. But what about the infinitely many other choices for directions? And there's nothing we can do about that. We can't specify those directions in this way. So we're going to need to develop a whole different way of talking about directions. And that new way of talking about directions is vectors. So in 2D, we're going to need vectors to specify directions. And we'll see that all of the variables that had direction in one-dimensional kinematics will now be vectors. Those are position, velocity, and acceleration, and also displacement. We don't use that as much. I guess I'll include that as related to position. And now when quantities are vectors, you know, we used to just treat them as a variable. Now they get this fancy new hat. They all get a new hat in two-dimensional kinematics. It sort of has this jaunty angle to it, like a sort of like a military beret. Okay, so in order to go into two-dimensional kinematics, we need some mathematical preliminaries. Like first, we have to figure out what the hell a vector is. That, you know, that'll be important. So we first have to talk about vectors. And in order to talk about vectors, I'm going to have to give a little introduction to trigonometry. Not very much, but we'll just have to do some trigonometry. Essentially, the trigonometry that we're going to have to do is understanding a little bit about what cosine and sine are, because we're going to have to use those two functions, the cosine of an angle and the sine of an angle. Okay, so for a vector, think of a vector as an arrow. So think of a vector as an arrow. With two properties. A magnitude. You can think of that as the arrow's length. And a direction. And the direction, you know, is where the arrow is pointing. So, like for example, this is a vector. Its magnitude is given by this length. And its direction is into the, you know, upper right corner. If you specify a coordinate system, you can express any vector as a pair of components. So these components, let's say one component is parallel to the x-axis and one component is parallel to the y-axis. So the way this looks is if this is the vector that you're looking at, and this is the coordinate system that's specified, you know, this is the coordinate system that you're most familiar with. And let me draw this a little longer. Okay, so So let's say this is the y-axis, this is the x-axis, this is the y-axis. Okay. Then the vector components are the lines parallel to the x and y axis that complete a right triangle with this vector. So this one is called the x component. And this one is called the y component. This sort of, so we're always, before we do math with vectors, we're going to turn them into components. We're going to express them as components. And this gives you your first idea of why we need to go into trigonometry. Trigonometry is about studying triangles. And in order to take this vector and put it into components, we're making a right triangle. And sine and cosine, we're going to see, are useful things. If you know something about an angle of the triangle and you know something about the magnitude of the vector, the length of that diagonal, the sine and the cosine help you find those components, those other legs of the triangle. One thing that is worth noticing, I'll bring this up again, but I guess notice finding the components of a vector is equivalent to finding the coordinates of a point. For example, if you have this vector and you want to find its components, put the tail of the vector, and actually go back to your notes for a second and just put this on the that first vector I drew. So this is going to be called the tail, and this is going to be called the head. The head is like the arrow point. The tail is where the feathers would be. So if you're trying to find the vector components of this vector, put the tail at the origin of the coordinate system. So there's the x-axis, the y-axis. The components then are going to be the coordinates of the point where the head is. Okay. So if the tail is at the origin, the components are the coordinates of the head. So this would be the x component. This would be the y component. And you could see in this case, the x component is going to be negative. You can see that because you know the x coordinate of this point is going to be negative, and the y component is going to be positive. Okay. Any questions about that? All right. So the trigonometry we're going to talk about trigonometry in general is the study of triangles. We are only going to be concerned with right triangles. And right triangles are triangles where one of the angles is 90 degrees. So for example, this triangle is not a right triangle. But this one is, okay? Because this angle is, so this is not a right triangle. In this example, you have two angles that are way less than 90 degrees and one angle that's way bigger than 90 degrees. This one is a right triangle because no matter what these two are, you can see this one is 90 degrees. And we'll use sine and cosine to relate the angles of right triangles to the side lengths. So if you have a right triangle, let's say the right triangle that we're dealing with is this one. In this case, the 90-degree angle, the right angle is this one. The side that like doesn't connect to that right triangle, the one that's directly opposite that right triangle, is called the hypotenuse. And so no matter what one of these other two angles you're talking about, the hypotenuse is always the same. It's the one that's opposite the right triangle. But in order to name the other two sides, we have to choose one of these other two angles to look at. So let's say, for example, that we're looking at this angle. We're going to call this angle theta, the Greek letter theta. The side that does not make up any part of that angle theta is called the opposite side. And the only side that's left, the one that makes up this angle theta, along with the hypotenuse, you know, two sides have to make up that angle, is called the adjacent side. And notice that if we were looking at the other angle instead, these two would switch. You know, what's called the adjacent here is the opposite of this angle. Okay, so now that we've defined these, we can come up with sort of working definitions of sine and cosine using this. It's just a sort of a stupid memory device, but somehow it seems to work really well.
The y-axis angle, does it have a specific name?
No, because they're not always aligned that way. The y.
Okay, right.
So memory device, SOHCAHTOA. It sounds like some bit of like Samoan wisdom or something. But what it means is, so SOH means the sine of the angle is equal to the length of the opposite side over the length of the hypotenuse. The cosine of the angle is equal to the length of the adjacent side over the hypotenuse. And the tangent of the angle is equal to the opposite length over the adjacent length. We're not really going to have any use for the tangent, but these two we're going to use all the time. One thing to notice for this class is we're going to talk, what? Oh yeah, sorry. So in this class, we're going to talk about angles in degrees, not radians. So anytime you're doing calculations for this class, be sure your calculator is set in degrees. If you don't know how to do that on your calculator, bring it up to me. And actually, a student did come in with a calculator. I couldn't figure out how to do it, but usually it's sort of the same in every calculator. Sure. Yep. Okay, so notice, set your calculator in degrees. Here's an example problem. Say that you have a right triangle with side lengths. So this is the 90-degree angle. And the side lengths are 4, 3, and 5. And let's call this angle theta 1 and this angle theta 2. First, what's the sine of theta 1? So sine is defined as the opposite over the hypotenuse. The opposite of theta 1 is 3. The hypotenuse length is 5. So the sine of theta 1 is 0.6. Second, what's the cosine of theta 1? Well, cosine is adjacent over hypotenuse. Which of these is the adjacent of theta 1? Yeah, 4. The hypotenuse is 5. So the cosine of this angle is 0.8. Then C, what is the cosine of theta 2? Cosine is adjacent over hypotenuse. What's the adjacent side for theta 2? The adjacent side, I switched up, so this is cosine. The adjacent side for theta 2 is 3. The hypotenuse is 5. So you get 0.6. And then the last one, what's the sine of theta 2? The sine is the opposite over the hypotenuse. The opposite is 4. Hypotenuse is 5, so you get 0.8. And you see here a relationship that's true for any right triangle. The sine of one angle is equal to the cosine of the other angle, and vice versa. And that always has to be the case because the hypotenuse never changes, and when you change angles, your adjacent and opposite flip. You know what I mean? So you can sort of imagine that trend has to happen. So this is the most the case that we're going to deal with the most often, will be given a vector's magnitude and the angle that the vector makes between either horizontal or vertical. And we're going to have to take that and express it in vector components. So to do that, let's say this is the vector. And let's say that we're given that it makes an angle with this horizontal of, in this case, let's say 45 degrees. And let's say that the length of the vector is 10. Then to find the components, find the counterclockwise angle from the positive x-axis to the vector. The tail of the vector needs to be at the origin. So in the case that I just did, if this is the coordinate system, there's the positive x-axis, there's the positive y-axis, there's the vector we're trying to find. We know that this angle is 45 degrees, but that makes a clockwise angle of 45 degrees with the negative x-axis. We want the counterclockwise angle from the positive x-axis. So the angle that we want is this one. Okay. So in this case, the way to think about this always, I would say, is remember that every time you get to a new axis, it's 90 more degrees. So it's 90 to here, 180 to here, but we didn't make it all the way to here. You know, we stopped 45 degrees short. So this angle is 180 minus 45. So the angle is 135. And then once you have that angle, the vector components are the length of the vector times the cosine of the angle, length of the vector times the sine of the angle. We're going to always write it one on top of the other like this, with the x component written on top and the y component on the bottom. So in the example I just did, the vector's components are 10 times the cosine of 135, 10 times the sine of 135. So you would enter, if you wanted to find the components of that vector, you'd enter into your calculator, you know, cosine of 135 times 10. And you should get out a value of negative 7.071, positive 7.071. Anyone who has a calculator here, why don't you just plug that in right now? If you don't get those values, probably the issue is that your calculator's in radians. Is that working out for everyone? Any questions about entering that in? All right. One thing to notice here is, so a positive angle is measured counterclockwise from the positive x-axis. You can always, if it's easier, measure clockwise from the positive x-axis and just call the angle negative, okay? So measure the angle clockwise from the positive x-axis. And just call the angle negative. So for example, this case that we just did, that is 135 degrees going this way. You could also enter it in as 180 plus 45 negative. So negative 225. Try entering that in. So 10 times cosine of negative 225, 10 times sine of negative 225, and you should get the same thing. Because in the example I gave, that was just the length of this vector. So that's just a choice you have. Like if a vector is given, and it makes, say, a 5-degree angle below the x-axis, you have the choice of entering it cosine and sine of negative 5 or cosine and sine of positive 355. Okay. One thing that probably, you know, this is going a little too fast for you to make this connection, but if you're reading back through your notes, you might sort of notice that this SOHCAHTOA definition I gave, everything is positive, right? This right triangle, I mean, you can't have negative lengths of things. But if you enter cosine or sine of certain angles, you get negative values. So how does that work out? Like, I gave this as sort of a definition, but that definition doesn't cover the negative cosines and sines. So in order to make sense out of that, you have to think of the unit circle. So I'll call this a more complete definition of sine and cosine. compared to SOHCAHTOA. And this more complete definition comes from the unit circle. It's called the unit circle because the radius is 1. You know, it has a radius that's a unit. So every point on the unit circle is a distance of 1 from the origin. That's a circle. You'll have to take my word for it. I always say that, but then I can never... I'm going to be drawing this circle for the rest of the class. You guys can go to the bathroom or whatever. At the bathroom, I mean. Okay, so if you measure your angle counterclockwise from the positive x-axis or clockwise from the positive x-axis and call it a negative angle. So let's say that this is the point that we're interested in. Measure your angle theta this way. Okay. Then the cosine, and let's call this point P. The cosine of that angle is the x-coordinate of P, and the sine of that angle is the y-coordinate of P. Okay, so then intuitively it sort of makes sense. If you entered in this angle, let's say that this angle is 225. Okay. So looking at where this falls on the unit circle, looking, eyeballing what the signs of these coordinates are going to be, would you expect the cosine of 225 to be positive or negative? Negative, because the x-coordinate of this point P is negative. And would you expect the sine of 225 to be positive or negative? Negative, yep. For the same reason, the y-coordinate of this point is also negative. And so that tells you, let's say intuitively, you know that if theta is between 0 and 90 degrees, the cosine and the sine, should they be positive or negative? Positive. If theta is between 90 degrees and 180 degrees, what should the sine of the cosine be? Yep, that's exactly right. So the cosine should be negative. The sine should be positive. And that's because between 90 and 180 degrees, the coordinates of all these points have a negative x coordinate and a positive y coordinate. Okay. Then theta between 180 and 270. Yep. And then the last one, theta between 270 and 360. What should be the sine of the cosine? So the cosine should be positive, and the sine should be negative. And that's something intuitive that you can do to make sense out of your answers. You know that depending on what quadrant you're in, you expect certain things from the cosine and the sine. And you expect certain things from the x and y components of the vector. for the same reason. Yep. The unit circle, yeah.
Yeah, you know how
Mhm.
quadrant one had all, and that all is positive, and quadrant
Mhm.
S, quadrant two.
Yeah, I think it's easier, to me at least, it's easier to have a picture in your head than to memorize like a data table kind of thing. Any questions about any of that so far? Okay, well, the next issue is now that we know how to do the components, maybe we should have asked this question before I started all this, but why do we need to know the components? Like, because maybe we don't. We do. So, you know, there are different ways to specify a vector as long as you specify its magnitude and its direction in some way. You know, there are a lot of equivalent ways. Why are we choosing to represent it in terms of components in a coordinate system? And the answer is that it makes a lot of mathematical operations much easier. And the mathematical operations that we're going to care about are adding two vectors and multiplying a vector times a number. And instead of numbers, we're going to call these scalars. A scalar is just a mathematical quantity that isn't a vector. It's just a number. Okay, so here's how to add two vectors if you know their components. So let's say that we're adding a vector AB to a vector CD. You keep the X components separated from the Y components and just add them together. So the X component of the vector that the sum of these vectors is A plus C. The Y component is B plus D. And that's your new vector. This, by the way, is called the resultant vector. And that would just seem like kind of, you know, like abstract mathematical whatever, except it turns out that if these represent two velocities, and like say that you have somebody, say that one of these represents the velocity of a ship going through the ocean, and this other one represents the velocity of somebody running on the ship, like going for a jog, and you want to know what the speed is of the person, like the actual speed, not just the speed that they're running, you know? You add these two together, you get these components, and those components are the vector components of velocity that someone would measure who's standing on the ground, you know? So it has like a physical significance. Okay, and to multiply a vector by a scalar. So let's say that we have this scalar k, and we're multiplying it by a vector whose components are a, b. You get a resulting vector where the x component is ka and the y component is kb. Also, one calculation that's often helpful is, given a vector's components, what's the magnitude of the vector? Well, if your vector, let's say your vector is called u, okay? The sign for taking the magnitude of it is absolute value. It looks like the absolute value of a vector. What you're really doing is calculating the length of that vector. And the way you do that is you square the x component, add that to the y component squared, and take the square root. So ux is the x component of u, and uy is the y component of u. And does anyone recognize this formula? Yeah, exactly. It's the Pythagorean theorem. You use it to relate the length of a diagonal of a right triangle to the lengths of the sides. And so if you think about what those vector components are, I first talked about vector components as side lengths of a right triangle. So really, that's exactly what you're doing. You're taking the Pythagorean theorem. Yeah, it took me a second to, yeah. So you're squaring the length of one component, one of the sides of a right triangle, adding it to the squared length of the other, the other side of the right triangle, take the square root, and that gives you the length of the diagonal, which is the magnitude of the vector. And probably the case where this is most useful is, velocity is going to be a vector. Speed is, when you're talking about 2 dimensions or 3 dimensions, an object's speed is the magnitude of the velocity vector. So if you come up with a velocity vector and then you want to know what the speed is, you do this and bam, done. Any questions about any of this so far? Okay. Here's an example. I'd like you to see if you can work through this. Calculate the resultant vector for this expression. 4 times the vector 6, negative 3.5, minus 2.5 times the vector negative 2, positive 1. Okay. And then why not find the magnitude too? Okay, so work on that together. See if you can work through that.